Hello, and thank you for stopping by. I'm so excited to introduce STEC's mild plasma technology today. What we offer is a next-generation surface modification solution. It enables new combinations of materials that are usually difficult to bond, while keeping the surface smooth and minimizing damage. In the next few minutes, I'd like to show you what makes this technology different, why it matters, and where it can create value in advanced electronics and materials manufacturing. Well, let's jump right in. Before I go into the technology, let me briefly introduce our company. STEC is an equipment manufacturer based in Shimane, Japan. We were established in 1991, and our philosophy is to create what has yet to exist in the world. We develop, manufacture, and sell automated equipment for industrial customers. Our experience covers analytical pretreatment systems, cutting machines, and of course, mild plasma irradiation equipment. Since our founding, we have supported manufacturers in industries such as steel, automotive, cement, biotechnology, and advanced materials. So, mild plasma is not a standalone laboratory idea. It comes from STEC's long experience in designing real industrial equipment and delivering systems that work in production environments. That is one of our strengths. We do not just propose a surface treatment concept. We build the equipment and the process around it. Now let me introduce mild plasma itself. Mild plasma is designed to overcome the limitations of material properties. For example, it enables direct bonding between fluoropolymer resins and ultra-smooth copper foil. It can also turn hydrophobic powders into hydrophilic ones to improve dispersibility. And it opens up the possibility of printing conductive ink directly on fluoropolymer materials. In short, this is a platform technology for solving surface-related problems in bonding, wetting, dispersing, and printing. So, how does it work? Mild plasma generates functional groups on the outermost surface of a material. This improves wettability and adhesion, while modifying only a very thin surface layer, just a few nanometers deep. That is important because the surface is activated without causing physical damage to the bulk material. When it comes to the key advantages, 4 points are shown here. 1. It can bond materials that normally do not bond. 2. It causes almost no change in surface roughness. 3. The surface modification effect can be maintained for years. And 4. It has already been proven in mass production processes. So, first off, mild plasma can bond materials that normally do not bond. It enables direct bonding across a wide range of material combinations, including resin to metal, resin to glass, and resin to ceramic combinations. And importantly, this is achieved without adhesives and without anchor bonding. Instead of relying on roughening, the bonding comes from chemical interaction between functional groups generated on the surface. For customers, this means more design freedom, cleaner interfaces, and new possibilities for high-performance material structures. Second, it causes almost no change in surface roughness. This is another major differentiator. Many conventional plasma treatments improve wettability, but they also roughen the surface. That can be a problem, especially when smoothness is critical. Take a look at the picture on the right. It shows water contact angle and surface roughness of PET after plasma treatment. It indicates that compared with other plasma treatments, mild plasma can minimize the surface roughness. In fact, with other plasma treatments, the surface often becomes rough. As a result, even if functional groups are generated, they may become buried within the material and lose their effectiveness. Also, as shown here for PET, the water contact angle changes significantly, from 79.9 degrees to 40 degrees, while the surface roughness changes only slightly, from 0.46 nanometers to 0.53 nanometers. In other words, we can create a bondable surface without sacrificing surface smoothness. Next, it can maintain hydrophilicity even for polyolefins such as PE and PS, which are usually challenging materials. A common concern with plasma treatment is aging behavior. In many conventional treatments, hydrophilicity drops over time due to hydrophobic recovery. The functional groups on the surface may gradually reorient, and that can naturally reduce adhesion over time as well. This is known as hydrophobic recovery. However, with mild plasma treatment, it is shown on the graphs that its effect tends to last longer. Mild plasma avoids excessive etching, so it creates a more stable surface condition. Now, let me move to applications. The first one is ultra-low loss CCL manufacturing process for 5G and 6G applications. Here, mild plasma enables direct bonding between fluoropolymer resin and ultra-smooth copper foil. Why does that matter? Because in high-frequency applications, roughened copper increases transmission loss. With mild plasma, bonding can be achieved without adhesive and without mechanical anchoring, while maintaining a smooth copper surface. Our record shows the peel strength of the bonded fluoropolymer to copper structure was over 10 newtons per centimeter, and transmission loss was minus 2.89 decibels per 100 millimeters at 80 gigahertz, compared with minus 3.29 for the conventional approach. The second application is printed electronics. Whereas fluoropolymer materials are attractive, they are also difficult to print on. Mild plasma improves the adhesion between metal inks or primers and fluoropolymer resin. As shown in the tape peel test, untreated samples peel off completely, while mild plasma-treated samples show no peel-off. I would also like to highlight that transmission loss of fluoropolymer resin substrates treated with mild plasma can be reduced to half compared with LCP substrates. This means customers can consider new process routes such as printing and plating to fabricate fluoropolymer resin substrates. The third is thermal interface materials. For TIM applications using boron nitride and other functional fillers, dispersion and interfacial adhesion are critical. Without proper surface control, you can get agglomeration and void formation, which reduce thermal conductivity. Mild plasma activates the filler surface in a dry process under vacuum. That helps improve wettability, enables more uniform dispersion, and supports a void-free structure. So here the value is better thermal pathways and potentially better TIM performance. The last one is carbon fiber. The left side shows that mild plasma makes carbon fibers hydrophilic. Before treatment, the contact angle is 92.2 degrees. After treatment, the water droplet is absorbed immediately, to the point that contact angle measurement becomes impossible. That improved wettability leads to better resin impregnation. On the right side, the cross-sectional SEM image shows the difference clearly. Without plasma treatment, you see multiple voids, and after mild plasma treatment, the structure becomes much more uniform and free of voids. To close, mild plasma is a practical surface modification technology that combines 4 key advantages. It enables direct bonding of difficult materials. It preserves smooth surfaces. It offers long-lasting treatment effects. And it has already been proven in production in Japan. So if you are working on advanced substrates, printed electronics, thermal materials, composites, or any application where surface chemistry is limiting your performance, we would love to talk with you. We are open to collaboration. Let's create what has yet to exist in the world together. Thank you for your attention.